Today we're going to talk about significant figures. Now, significant figures are very important. The reason they're important in science is because all the numbers in science, for the most part, come from measurements. And significant figures means the numbers that you can rely on based on your measurements. In math class, you don't have to worry about significant figures because for the most part in math class you're talking about a theoretical concept of a number, the infinite precision of a theoretical number. When you say 2 in math class, you really mean 2.0000000 out into infinity. Exactly 2. But that's not true in science class. In science class, maybe you mean 2.0, or maybe you mean 2.00, or maybe you mean 2.000. And it's different because all these numbers have a unit attached. Maybe it's centimeters or meters or seconds. And these zeros all have significance because of the precision of the tool used to measure them. Let's take a look at some of these tools. Here, for example, is a graduated cylinder. You'll notice the cylinder is marked every milliliter, 1, 2, 3, 4, 5, and so on. But there's also these little markings in between. Okay? I've blown it up here, but let's use the magnifier and blow it up even more. Alright, so what you'll notice is, let's count. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 markings there between the 5 and the 6. So that means each marking corresponds to 0.1 milliliters. This blue here is supposed to represent some liquid within the graduated cylinder. We know it's more than 5 milliliters. We know it's less than 6 milliliters. We can tell this even more closely by looking at this expanded part, by counting these little lines. Notice it's this curve here. That's because water, when it's in a graduated cylinder or a beaker or something like that, always has that curve to it. The reason is because the water is attracted to the sides of a container. So what you want to read is the lowest part. That's called the meniscus. You always want to read the meniscus. That's this low part right there, not the high part over here. So if I'm looking at this meniscus, I'm going to count. I'm going to say 5.1, 5.2, 5.3, 5.4, 5.5. The most exact measurement that I can read is 5.5 milliliters. But I'm not done. I can look at this and say, I don't think that's exactly on that 0.5 line. So I can estimate a digit. Now, I could estimate a 0. I could say that's exactly on that line. I'm going to say 5.50 milliliters. But in this case, I think I'm going to say that's a little above it. I'm going to say 5.51 milliliters. These are my significant digits. They are directly related to how many markings are on my graduated cylinder. Let's look at the next one. This one is what's called an Erlenmeyer flask. You see the shape of this? That's an Erlenmeyer flask. And you'll notice my markings aren't nearly as good as they were in the graduated cylinder. I have a marking at 100, 200, 300, 400, and I have a marking that's every 50. 300, 350, 400. So when I'm looking at this, I can say to myself, it's a little below the 400. But what I cannot say is that it's 399 milliliters. Can't say that because I don't have the markings. I've got 300, 350, 400. The only thing I can really say about that liquid level is it's somewhere between 350 and 400. So when I'm estimating a digit, it's really the digit in that tens place that I'm estimating. I can say 390 milliliters, or maybe I really want to say it's 400 milliliters. But that's my best estimate. That's the best I can do, because that's all I've got, is these really, really wide markings. This is, again, what significant figures mean. It's all about the markings on my reading device. This one's a meter stick. I'm looking here at the metric. This is 5 centimeters. This is 6 centimeters. Again, my markings are in tenths. So I can say 5, 5.1, 5.2, 5.3, somewhere between 5.3 and 5.4. So I'm going to estimate 5.35. Not forgetting my unit of centimeters. This one's even harder to tell. This one is a thermometer. This side's Celsius, this side's Fahrenheit. Let's stick with the Celsius. This is science class. So now we've got markings that give me the ones digit. 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So I can only estimate the 10 spot here. I can say 25.8 degrees Celsius, something along those lines. But this is my estimated digit because I can read the ones digit exactly. This one's my estimated digit. Here's another thermometer. Once again, we'll read the Celsius scale. This is terrible because I've got no markings at all between the 10 and the 20. So all I can say is estimate the ones digit. I can say maybe it's 12 degrees Celsius. But this has to be my estimated digit because that's all I can read for sure. The 10 and the 20 are all I can read for sure. So that's my estimated digit. So let's make a rule here. The rule is when you're reading something, some instrument, you want to report all the digits you can read exactly plus one estimated digit. Only one estimated digit. That's it. One estimated digit. If you go, it's about a quarter of the way through, I'm going to estimate 0.25. You can't do that. That's two estimated digits. All you can estimate is one digit. Okay? Everything you can read exactly plus one estimated digit. Now, what if you're reading a number? You're looking at a number someone else reports from their laboratory experiment. You want to be able to look at this number and know what they mean. How many of those digits they are reporting are significant. So let's go over some rules here. Rule number 1. All non-zero digits are significant. Okay, that's rule number 1. If you're looking at something someone else has written and there are no zeros in it, you can be pretty sure all those numbers are significant. It's when the zeros come in that things start getting a little hairy. Number 2, we'll start with the easy rules. Zeros at the beginning of a number are never significant. Okay? So something like 0.3 milliliters. 0 is not significant. You only have one significant digit here, and it's that 3. 0.003 milliliters. Still only one significant digit, and it's the 3. These guys, not significant. All they are placeholders. They're there to tell you where the 3 is in relation to the decimal point. Yes, they're important. Yes, you definitely need them to know what that number is, but they are not significant in the chemical term. Okay, significant doesn't mean important. Significant. There is only one significant digit there. 3. Zeros in between non-zero digits are always significant. All zeros in between non-zero digits, always significant. So if you have 303 milliliters, you've got 3 significant figures there. All 3 of those significant. It doesn't even matter if you have more than one zero. You have 5,005 milliliters. You have 4 significant figures. All zeros in between non-zero digits are significant. Rule number 4. Zeros at the end of a number after a decimal point. Always significant. Always significant. Let's think about an example to that. If you have 0.70 centimeters, that's 2 significant digits. These 2 guys are both significant. Now you say to me, wait, that doesn't make sense because that 0 isn't very important mathematically. If I plug that number into my calculator, 0.70, the calculator would drop that 0 right off. It's not an important number at all. Absolutely right. Mathematically, it's not important. But it is significant. It's significant because the only reason someone might have had to write it is to tell you this was their estimated digit. They really mean it's 0.70 centimeters. Their 7 was not estimated. It was the 0 that was estimated. That's why zeros at the end of the number after a decimal point are always significant. Rule number 5. This is kind of a weird rule. Zeros at the end of a number without a decimal point may or may not be significant. Okay? It depends. It depends on the circumstance. Okay? Let's think about that for a minute. Let's say you have the number 5,000 milliliters. The question is, which one's the estimated digit? These zeros are all important mathematically because they say that the 5 is in the thousands place. But where was the estimated digit? Did the person have the glassware to read to the ones place? Is the ones place the estimated digit? Is the tens place the estimated digit? Is the hundreds place the estimated digit? We don't know. That's why I said may or may not be significant. We have no idea looking at that what is the estimated digit. So, what we need are conventions. Something to tell you, the reader, which one I mean as my estimated digit. Okay, so the rule is, if I only have one significant figure here, I don't do anything. I just write this 5,000, and the only thing you can be sure of is that one sig fig. If, on the other hand, I want to say I really meant all of them, I want this to be 4 significant figures. As an indication of that to you, the reader, I would write 5,000 with the decimal point. If I explicitly put that decimal point in, I am telling you that I want that to be 4 significant figures. Okay? What if I want one of them in the middle? The convention is I put a bar over the last significant digit. So if I do that, then I have 3 sig figs. And if I do that, I only have 2 sig figs. All of which is really annoying and confusing, right? So, instead of doing any of that, what we can do is scientific notation. Okay, so that's rule number 6. Scientific notation. Everything to the left of the time sign in scientific notation is significant. So if we go back to that 5,000 again, if I want it to be 1 significant figure, I say 5 times 10 to the third. If I want it to be 2 significant figures, I say 5.0 times 10 to the third. If I want it to be 3 significant figures, I say 5.00 times 10 to the third. And if I want it to be 4 significant figures, I say 5.000 times 10 to the third milliliters. Much, much easier than this whole convention of where am I going to put the decimal point? Am I going to put a bar over the top? Much easier just to write it in scientific notation. Then I have no ambiguity about how many significant figures I have. Okay, so we've got 2 separate things to think about here. When you are writing your data down, you want to put everything you can plus 1 estimated digit. Everything you can read exactly plus 1 estimated digit. Or if you are reading someone else's numbers, then you follow all these rules I just listed to determine how many significant figures. Now, there is one exception, and that's exact numbers. Exact numbers are numbers by definition, basically. Let's say you are, or by counting. If you can count it, like you've got 5 pennies, and you're figuring out the average mass of those pennies, you would have all of your masses, right, that you would add up. Mass 1 plus mass 2 plus mass 3 plus mass 4 plus mass 5 divided by 5. That 5 is an exact number. You counted it. There was no estimation needed. You said I had 1 penny, 2 pennies, 3 pennies, 4 pennies, 5 pennies. Look, I've got 5 pennies. That really is 5.00000 out to infinity, just like in math class. So that guy doesn't count. That's an infinite number of significant figures. Okay? Infinite number of significant figures. And something by definition. So 100 centimeters equals 1 meter. Exact numbers. That is 100 by definition. So you don't have to say, that's 3, or there's no decimal point on it. There's only 1 there. There's only 1 there. You don't have to say that. Anything that is by definition exact number. Infinite number of significant figures.